I got lots of different follow-up questions. So one of the ones that got asked was to talk about the graph. So basically, I don't have any questions about it, but we're just going to start from the beginning. So first of all, this graph usually says something like graph of ideal solutions involving, this could be liquid Q and water. So down here on the bottom, well, the only information we have is this big X, which is supposed to be mole fraction, but it was just going to say X. So it's up to you to remember that that is mole fraction of Q. And so what this graph really is trying to do is talk about, I'm just going to do 6 of these. So there's a point basically here where in a beaker, there was no Q, okay? 0% Q. If there's no Q, the other liquid that's there is water. So this is basically 100% water. And that's what's happening here at this first point, is 100% water. So for this solution that is 100% water, we measure the vapor pressure. So this y-axis is supposed to be pressure. So that means that this point on the graph that touches this y-axis is in fact the vapor pressure of pure water. So that's one point on the graph. Well, if we have a place where it's 0 Q, but 100% water, we certainly on the complete opposite end have a point where in solution, it is 100% Q. The only thing in here is Q, nothing else is in here. There is no water. The only thing present is Q. So that means that this point over here, where this solid line touches the y-axis here, is the vapor pressure of pure Q. Now, along this line, we're going to go ahead and we're going to try to say that right here is another solution. Now, there are different solutions all along this line, but I'm trying to pick one where we can hopefully see it. And here, we're going to assume that this is the place where I have some amount of Q. So I'm along this x-axis. So I have about 25% Q. And I have 75% water. So the vapor pressure that I then get at this point is going to be a combination of Q and water vapor. I'm going to have both. But one of the things to note is that when I say 75% and 25%, that is also 0.25 mole fraction Q and 0.75 mole fraction water. And these are in the liquid phase. Since I'm on the x-axis, I'm dealing with the liquid. But I want to be able to measure what's happening in the vapor phase. So I have a few points that can tell me information. So this point here would give me the vapor pressure of Q when there's 25% Q. This point here would give me the vapor pressure of water when there's the 75% water. And this point here, if I've drawn them correctly, are just these 2 points added together. So let's actually try to make them look a little bit different so I can draw that a little bit better. So my X is still my vapor pressure of Q. We'll go ahead and make Y the vapor pressure of water, and we'll go ahead and say that this is point Z. So my point Z is in fact my vapor pressure of the solution, but that should be equal to that vapor pressure of Q plus the vapor pressure of the water. So This graph is in fact trying to show you basically 100 different solutions, starting on the left where there's all water and no liquid Q. And then we could move just a little bit and say that I have 1 part Q and 99 parts to 99 moles of water. And then I could move 1 more and say I have 2 moles of Q and 98 parts water, and then 3 moles of Q and 97 parts water, all the way until I get to this red line where I say I have 25 moles of water and, 25 moles of Q and 75 moles of water. So this x-axis here is trying to talk about the liquid, but we are then trying to measure and have information about what's going on with the vapor pressure. So one of the other things that we can ask about with this graph are things like which one is essentially overrepresented. And you can do that in a couple of different ways. One of them is to just look at the halfway mark. So I know we could argue about exactly where my halfway mark is, so I'll make it kind of thick. But what you can see is if I'm roughly halfway, so I have roughly half of my moles are coming from liquid Q, half of my moles are coming from liquid water. What I should be able to notice then is that that's not true in the vapor. That's true for the liquid, but that's actually not what's happening in the vapor phase. So sorry, I'm trying to find some more colors because I like colors, but we are, magenta, there we go. Sorry, it doesn't matter. So what we're trying to do is say that I have half of my moles are coming from each liquid, but when I look, I can see that I have here, again, that vapor pressure of Q, and then down here lower is the vapor pressure of the water. So when I have an equimolar amount of the liquids, I'm gonna write that phrase down. When I have equimolar liquid, I have more vapor or more gas from Q. It's because Q has the higher vapor pressure, which we can just see by trying to take a look at these places on the axis. Because Q has a higher vapor pressure overall, it's going to be overrepresented in the mixture. So no matter how many moles of the liquid of Q I have, that liquid gives off so much gas, I'm just going to see more of it in the vapor phase. So this is like if you were taking something like water and rubbing alcohol. Rubbing alcohol has a smell to it, or water and a perfume. Perfume is supposed to be really fragrant. You're supposed to be able to smell it really well. The water vapor is still there, but you're not going to see as much of the water vapor as you see of whatever that other volatile liquid is. So hopefully that helps with some of the labeling. There was one more thing I wanted to make sure, 2 more things actually, that I wanted to make sure I pointed out. So when I say that the vapor pressure of Q is greater than the vapor pressure of, and this should really be pure, like the pure solvents. So dealing with pure liquids. Dealing with pure liquids, my vapor pressure of Q is going to be greater than the vapor pressure of water. That also means something else, which is that water has the stronger intermolecular forces. So even if I don't know what Q is, the fact that water has the lower vapor pressure means it has the stronger intermolecular forces. When we try to take a look at that, keep in mind that what we're trying to say is if this is my water, then the better those molecules hang on to each other, the more of it stays in the liquid phase. The worse they are at hanging on to each other, the more of them essentially can escape. So if I have my lovely liquid Q, what I'm trying to say is that Q just doesn't hold on to each other very well. So you're going to see a lot of vapor particles hanging out in the gas phase, a lot of particles in the gas phase in Q, because it's going to have lower intermolecular forces. The water is going to have stronger or higher intermolecular forces, and that is why water actually has the lower vapor pressure. So that was one of the things I wanted to talk about, was the fact that those two things are related to each other. The intermolecular forces are the reasons why your vapor pressure is either higher or lower. Okay, the last thing I wanted to talk about was looking at one other point on the graph, which is this lovely point. So this is the other point that everybody likes to look at. So I just wanted to address it. Sometimes we ask questions about this point and sometimes we don't. We're going to refer to this as point A. So A is just the place where the pressures are equal. So it is where something is equal, but it's where the gases are equal. It's not where the liquids are equal. So just keep in mind that usually we have a tendency to ask about equimolars of the liquid, which then in that case, we're trying to deal with the x-axis, and we're trying to deal with that mole fraction idea. Wherever it is that those lines cross each other, it does mean something, but it's the place where the gases are equal. So oftentimes people have look for equimolar, and that place where the lines cross is so incredibly tempting. And again, it does mean something, but it's not the liquid. When you're up, when you're no longer hanging out on this x-axis, but you're actually up in the graph, you're looking at the pressure. So anything up here is trying to deal with what is the pressure given off by the liquid. So this graph is strange. It is likely something that y'all have not seen before. So do take some time. We ask questions about it every single year. So this is one of those good news, bad news, where yes, we will definitely ask you about this. Good news is we're only going to ask you one question about this, but it definitely does come up. What else can I do? So one of the other things, so someone's talking about the conceptual meaning, dealing with this graph. I'm going to hope that that is helpful, and hopefully drawing some more pictures where you do see that the vapor is made up of both liquids, each liquid contributing, and this notion that, again, we are trying to deal with a whole bunch of different solutions. So they are, in fact, a whole bunch of different solutions all happening. I didn't talk about what vapor pressure is in this video because I did that yesterday. So I'm trying not to duplicate too much, but these are just some of the questions that my class asked me. So one of these questions actually does relate a bit to vapor pressure. So why is it that when boiling point increases, freezing point decreases? So this whole notion of my boiling point increasing and my freezing point decreasing, and why? And the thing is that these are for two different reasons. They both have to do with the solute, don't get me wrong, but they are, in fact, the words we're going to use to describe this different. So first of all, we were talking yesterday about the fact that if I am talking about vapor pressure, that as I increase temperature, I increase vapor pressure. So if I'm looking at this being at 25 degrees Celsius, I have some vapor. And if I went ahead and could draw the exact same size of everything and the same amount of liquids, but now we'll bump this up to 50 degrees Celsius, I should expect to see more. So I had 4 particles before, now I have 6 particles. So as temperature increases, my vapor pressure increases. This essentially happens, we're going to go ahead and say that this is water to make our lives easier, because once we get to 100 degrees Celsius, my vapor pressure is going to be at 1 atmosphere. So basically this vapor pressure goes up and up and up and up and up until finally my vapor pressure is 1 atmosphere. 1 atmosphere is what our atmospheric pressure is. At that point, the atmospheric pressure is not going to be able to help contain or push together the molecules anymore. And the only thing I'm going to have are vapor particles. So as temperature increases, vapor pressure increases until you finally hit the atmospheric pressure. And at that point, everything boils and you have gas only, because the vapor pressure is equal to the atmospheric pressure. That's also why when you talk about things like boiling water like on tops of mountains, the atmospheric pressure is lower. So you don't have to have as high of a temperature to get the vapor pressure to be equal to the atmospheric pressure, because the atmospheric pressure is not as high. Or why you can set up chambers where the atmospheric pressure is super, super low, but you can do it in like a small closed environment. If you drop that atmospheric pressure, your boiling point doesn't have to be nearly so high, because you can change your pressure. But we as human beings are usually at 1 atmosphere. So that's usually what we're talking about, is that notion of 1 atmosphere. So the thing is that when we now want to go back and mention solutes, so if I'm talking about this for vapor pressure, solutes are basically going to block access to particles of the liquid being able to access the vapor phase. So basically, we get this vapor pressure lowering with solute being added, because now there's not as many places for those water molecules to escape. So if I come over here and I look at this one, I again should have a whole bunch of spots where I have now all of this solute hanging out, and I'm just not going to have as many particles in the vapor phase. So because of that, since my vapor pressure is lower, again, at all temperatures, no matter what, the goal is still to get the vapor pressure to the atmospheric pressure. But since I have to deal with all those pesky little solutes, I'm going to draw them here down at the bottom. So we're going to assume that the water boils off. This can't, and we're left with some sort of solid behind. This can't happen anymore at 100 degrees Celsius, because I didn't have as high of a vapor pressure at 25 degrees Celsius or as high of a vapor pressure at 50 degrees Celsius. So I'm going to need an even higher temperature. We'll just go ahead and go with like 102 degrees Celsius to actually make that same thing happen. So we're still looking to raise the vapor pressure to the atmospheric pressure, but because of the vapor pressure lowering effect, your vapor pressure has farther to go, essentially. Yeah, just has farther to go. So this is kind of like if you're trying to think like of a commute in between 2 places, and usually you start from like 5 miles away. We're now starting back from like 7 miles away. Like it's the vapor pressure is lower to begin with, and it stays lower that entire time. Or maybe I should say that you originally were driving in a car and now you got slid to a bicycle. And so you just need to put in more effort to get to where you're going, because you don't have the exact same mode of transportation. These are not great analogies, but the idea again is that your vapor pressure is lower, and because the vapor pressure is lower throughout all of those temperatures, you're going to need more heat to get the vapor pressure high enough to equal the atmospheric pressure, because that's still where the boiling occurs. It's still where boiling happens. So boiling is all about vapor pressure. Freezing point is not. So when it comes to freezing, keep in mind that what has to happen So I'll go ahead and draw some water molecules. I'm going to omit their lone pairs just for some simplicity's sake. But when water freezes, it actually forms a pretty lovely crystal lattice structure. Part of the reason why you can, in fact, get like really lovely clear ice cubes. You can get a really beautiful lattice structure going on. Go ahead and so so for something to freeze, so basically freezing needs a lattice or order or neatness. But the thing is that this is my lovely pure solvent here. And the hard thing is that I'm going to copy this, is when I have solute, that's can't always happen like that. I have all of these little things in the way. So I'm going to erase this for a minute. And I just have this giant solute thing happening in here that's just getting in the way, and it's mucking up the lattice. So essentially, because I have physical, so that's supposed to be my solute, my great big pink X. So essentially, it's a physical barrier. It's a physical barrier to forming a lattice or ordered packing, because you've got something weirdly shaped in there. I don't know how many of y'all have had to like pack up for a move recently, but whenever you're trying to like stack things in a box and you're like, okay, I got this thing and I have this thing and I have this thing, and look at how nice and neat they are. And then someone hands you something like a frying pan and they're like, that's supposed to be a pan, just deal with it. It's not a very good pan. And someone's like, here, now put this pan in there. This thing's got such a weird shape, right? So now if I'm trying to pack stuff into this box, oops, I just want to copy and paste, and do my best to try to copy this really terrible looking pan shape I made into my box. Can I rotate this? Whoop, no, but I can make it bigger. Great. And so now I'm trying to pack things, but now I got this weird stick thing in the way. And now all of my packing is just ruined because I can still pack around it. But right, I've got weird gaps now because that object is just such a funky shape. It doesn't match everything else that I had. And that's what happens in freezing. So you basically need even colder temperatures. You need those molecules to slow down even more for them to actually start forming order and packing together, because you've thrown in such a strange other object. And as you can imagine, some things will not be as bad as others, but it is the physical barrier to freezing that causes that to happen. One of the questions I got asked was identifying exothermic and endothermic reactions. And what I would really like to look at is actually a list I made for my class hanging out in the slides for chapter 13. Because I basically tried to go ahead and make a list in here. So when I'm looking for is just a copy and paste list, but I got to find where my copy and paste list is of endothermic and exothermic. There you are. So there are a lot of different ways to know if something is endothermic or exothermic. Here is the list I made. There is actually another thing we could add on to this. So exothermic, I have that it releases heat, that you have a negative value of enthalpy, that the beaker, quote unquote, gets hot, that products are lower in energy than reactants. So we've seen those little graphs that might just have some reactants over here and some products down here. So that notion that your products are lower in energy than your reactants, that bonds are being formed, or that interactions, intermolecular forces are being formed. We could also add one more thing onto this, which is that heat makes a solution less soluble. This would also be an indication of an exothermic reaction. If you made the solution warmer and you got a precipitate, if you made the solution warmer and fewer things were able to dissolve, that would also be indicative of an exothermic reaction. So for an endothermic reaction, as you might imagine, it's the opposite of all of these things. So an endothermic reaction, endo, within, exo, exit, leaving, endo, within, absorbs heat, positive value of enthalpy, or that positive delta H value. The beaker gets cold. Products are higher in energy than reactants. So here's my reactants, and here's my products up here on an energy diagram. And then either bonds are breaking or interactions are breaking. And then again, we could add here that heat makes a solution more soluble. So the warmer your solution is, the more soluble an endothermic solution, heated solution will be. So we could actually add one more thing under exothermic. Another where you might know something is exothermic is gases dissolving in liquids is said to be exothermic. So that's actually another way you would know that the reaction overall was exothermic, is if I had something like water plus carbon dioxide as a gas going to, I guess we'll draw this as aqueous carbon dioxide. So as you put the water and carbon dioxide together, that is an exothermic reaction overall. It should have all of those other components that we were describing. Actually, not this last one. The forming bonds or interactions, this is one that does not have to happen in order for it to be an exothermic reaction, but if you are forming interactions, then it is exothermic. So not all exothermic reactions have bonds being formed, but if you are forming bonds, that particular action is exothermic. To say everything correctly. So hopefully that helps. Unfortunately, I have to go to class. So this is going to be in multiple pieces. That happens to me sometimes. Thanks for reminding me.